Oh, hey. I'm here inside a lab at the University of California, San Diego. A physicist here. His name is Ivan. Now, where is he? He's working on a tough question. How to make things small. But he's not the only one trying to do this. There are researchers all over the world who are working on this kind of stuff. But Ivan's trying to make something smaller than ever before. And besides, he's my pal. So how small are we talking about? Incredibly small. In the jargon of science, we're talking about the scale of nanometers, or 1/1000th of a meter, the ever-popular nanoscale. You hear it all the time these days. Nano this, nano that, but what does that all mean? Well, let's see. How can I explain? Oh, hey, Ivan.
Here, I'll help you.
Ow. Thanks, pal. An average human hair, kind of like this one, seems pretty small. Well, no, it is pretty small. But it is about, 80,000 nanometers wide. So the scale of nanometers is way small. There's no easy way to ever see anything at that scale. Let's make things a little bigger so you can get an idea of how small things in the nanoscale really are.
Now where was I? Oh yeah. Remember our hair? It's a whopping 80,000 nanometers wide. So, how many atoms are in it? We can figure this out. First, we calculate the volume of our piece of hair in cubic nanometers. We use a little geometry here, but that's easy. That gives us a huge number. Then, we divide that number by the volume of an atom. Now, on average, there are about 125 atoms in each cubic nanometer, which is a tiny number. So, we end up dividing a huge number by a tiny number, which gives us this number. Look at this. How can there be this much of anything? That's a lot of atoms. How many? Let's see. I need something small.
Peanuts! Peanuts!
What the? Oh well. One, over here.
Got it.
Thanks. Hey, don't you own the Padres?
I do.
Why are you up here selling peanuts?
Well, you're buying, aren't you? We got to pay for the ballpark.
Maybe I should buy two. Hey, thanks. Perfect. If each atom were, say, the size of this peanut here, that would be enough peanuts to completely fill this ballpark. Now that is one heck of a bowl of peanuts. Whew, I'm gonna get thirsty. I wonder if that guy sells sodas too. Anyway, we could easily fill this entire stadium, and there would still be enough peanuts left over to fill every ballpark, every stadium, every sports arena, every ice rink, field house, and gymnasium on Earth 1,000 times over. And still, the particles that make up those atoms are even smaller, only thousandths the size of our average atom. And with all this, we're still only talking about the number of atoms in a single strand of hair. Even so, this tiny scale is real. As real as, well, baseball and everything else we know. So why are Ivan and people like him working with such tiny things? Because when things get small, Ivan and his friends can do things that can seem unreal. Things that can seem like magic. Pretty neat trick, eh? Wouldn't magicians love this one? It's even stranger, because all we know is that the ball disappears on one side of the wall and appears on the other. But even stranger than that is it's not magic. It really happens. How do you do it? Well, you just need a small enough ball, of course. How small? Well, here we go again. As you know, atoms make up molecules, and molecules make up bigger pieces of plastic and wood and concrete and plaster and everything else in the ball in the wall. And when we look at or deal with matter at that scale, it behaves the way we're accustomed to. Well, most of the time. Very funny, guys. However, when we deal with things on a small enough scale, matter can obey another set of rules. At this scale, the parts that make up atoms, let's say an electron represented by our ball here, can get through the wall. No magician can do this trick, but Ivan and his friends can. That's because he works with things on the nano scale. Imagine that the balls Ivan uses are electrons, which are only tiny parts of atoms, and the wall is just a very thin layer of atoms. This is the scale where matter can obey a different set of rules. Ready, Ivan?
Wait a minute, Ivan! What you said is correct. It's just too darn simple. As scientists, we have to describe things in terms of equations so that we can make predictions. So we need quantitative descriptions. What we use is the Schrödinger equation. Now this looks pretty complicated, but it isn't. Every one of these terms actually means something. For example, this term describes the wall. This term actually describes the electron. And this final term describes which way it's going, how fast it's going. And so we can go back and do the experiments in a quantitative way to understand this tunneling phenomenon. Are you ready? Do your trick.
Working with electrons and very thin layers of atoms, Ivan and his friends can pull off this trick. It's something called quantum tunneling. Pretty neat trick. But so what? These are effects that no one will ever see. They happen on the scale of atoms. And remember how small atoms are? What makes it so interesting isn't just that this trick can happen. It's that Ivan, and people like him, can actually work on this scale. And not only that, they can engineer things at this scale. Ivan made these dots quite a few years ago. Each of them is about 1,000 or so atoms on a side. Here's another way to look at it. With words as small as the ones Ivan made, you could write a little ditty, say something like, War and Peace, on the head of this pin. And you'd still have room for Crime and Punishment and Tale of Two Cities. Look, the collected works of Tolstoy, Dostoevsky, Voltaire, Shakespeare, and quite a few others. I got 'em all. Now, how am I supposed to read these? The point is, when you make things this small, things get strange. That's really why Ivan makes them, to see what gets strange. Things like this. Magnetism. It's already strange enough, but it gets even stranger on the nano scale. It helps if we can understand how magnetism works in the first place. Well, that part isn't really that strange. It's actually pretty simple. Magnetism is caused by spinning electrons. You can think of it like this. Imagine this is a spinning electron. Now, electrons carry an electrical charge, and a spinning charge, in this case, a spinning electron, creates a magnetic field. The thing is, electrons always spin one of two ways, either up
like this one, or down, like this one. We don't really know if they spin up or down. It's just a convenient way of saying that they have two different possible quantum states, also called spins or magnetic orientations. If we look at the structure of a material, we can actually see these magnetic orientations, or, in other words, spins, of its electrons.
That's just what we're seeing here. These different shaded blobs are actually clumps of atoms in which all the electrons are spinning the same way. They're called domains. So in a way, when we look at these domains, we're seeing a bunch of tiny magnets. On average, there are a few thousand atoms or so across. But still, that's a clump of billions of atoms, and that's big by Ivan's standards. So he wants to make them smaller. So what happens if a magnet is smaller than a single domain? Well, even though the electrons in the atoms have the same spin, and this little pile of atoms has one magnetic field with a north and south end just like any other magnet, its north end won't stay pointing north. It's like it's very nervous. It just flips around and points wherever, changing all the time. Thus, it can't exert any magnetic influence on anything else. In a sense, it isn't magnetic. But could it be made to calm down and hold still?
Could it be made magnetic? That is Ivan's next big trick. To make this domain hold still. If he can do that, he'd have the tiniest magnet ever known. In a way, that would be like taking an elephant and shrinking it to the size of a peanut. Or maybe a bag of peanuts. That's because the smallest magnet we have today is the size of an elephant compared to the one that Ivan wants to make, which would be the size of a peanut. But to make the trick even harder, these are the elephants Ivan wants to shrink. Remember these? He needs to shrink his dots just a little bit, by a factor of about 1,000, so his little dots are only about 15 or 20 atoms on a side. So, how's he going to do all that?
Not by wrestling elephants, I assure you. Come on, let me show you.
It's not quite what it looks like.
Oh, hi there. Is the music too loud?
So, what you working on?
I have just transferred an array of our latest nano-structured chemical field effect transistor devices from the load lock into the ultra-high vacuum section of the molecular beam epitaxy machine here, the MBE.
Oh, that's what I thought. And then what are you going to do?
Oh. The devices will be coated with a number of metallophallocyanines that contain bulk substituent groups to help us achieve a desired microstructure. I'll be coating the individual elements of the array using a floating shadow mask positioned within 10 micrometers of the array. The mask will be moved in situ without breaking vacuum, exposing one array element at a time.
Well, yeah, that's what anyone would do. So, why are you doing all this?
Because I love it.
Don't we all? But why are you doing the mask in situ metallo whatever thing?
Oh, that, well, we want to see whether the phallocyanines will act as the channel of the field effect transistor and whether the microstructure will improve the diffusivity of the analyte chemicals when we test the FET as a chemical sensor against analytes.
Well, of course. That makes it perfectly clear. Did you get all that? So here it is. Ivan's elephant shrinking device.
Well, obviously he isn't shrinking elephants. But he can very carefully control the layering of atoms to make substances that he wants to work with. He can do all this because this chamber allows him to remove just about all the atoms so that he can work with only the ones that he wants. Let's see. How can I explain? What the heck am I supposed to do with this? Oh, okay. I'll give it a try. Outside the chamber, everywhere in this room, and I mean everywhere, all over me and everything else, there are millions of atoms colliding with everything each second. But inside the chamber, it's a different story. Uh-oh.
Besides the fact that I need a spacesuit to survive in here, I would have to wait 3 hours until a single atom settled. Anyway, with so few atoms in here, Ivan can engineer things like his dots, very purely and at the size he wants. So, just what does he do with this thing?
Hey, come back! I'm not done yet! What he does is, he uses PMMA to make a shadow mask, just like that guy in the white lab coat. What the heck is PMMA? You're probably more familiar with it.
Here. Here. Or even here. It's the same material that's in plexiglass and lucite, but Ivan and his friends use it a little differently.
Hey, you!
Whoops. Come on, I'll show you.
They can make holes in it with an electron ray gun. No kidding. The electron ray literally changes the structure of the molecules so that they can be disintegrated later.
Here's a piece of it. Polymethylmethacrylate. It doesn't look like much, does it?
That's because it actually isn't much. On this disc, there is a very thin film of polymethylmethacrylate. Clearly, this won't be stopping any hockey pucks. But if we look at the same material close up, I mean, really, really close up. I said really, really close up, didn't I? This is the polymethylmethacrylate mask with holes that were drilled in it by the electron ray, and it just might be the stuff that helps Ivan shrink an elephant. This mask here is on top of a layer of silicon, or whatever special material Ivan wants to experiment with. Then, he and his cohorts use the MBE chamber to put magnetic material into these holes. He deposits the material a few atoms at a time. Then, he removes the mask. Hopefully, when he's done with that, he has little dots, nanodots they're called, left behind. If things work out right, this dot will be about 50 atoms across and maybe 15 or 20 deep, or a pile of 30,000 or so atoms. It would be a pretty good trick, because it's about as small as you can make things and still be pretty sure that there is anything there at all. But as good as this trick is, the real trick isn't just to make these dots, it's to make the magnetic orientation in the dots point in one direction and stay that way. It's something called pinning. That's right, like pinning an opponent in wrestling. Didn't he say he wasn't going to wrestle? Regardless, no one has been able to pin individual dots like these. Ivan thinks the key might not just be what they are stuck to, but how they are stuck. What do I mean? He thinks it might have something to do with how the atoms actually touch. Those seem like some pretty fundamental and kind of simple questions, but we don't have any answers to them. So, where does that leave Ivan? Still trying very hard to perfect his magic trick. Why? Well, he loves to do it. But really, he'd be doing something that's never been done before. He'd be starting something new. Which brings us to the second reason.
Before 1960, no one, not even Ivan and his hepcat friends, could have told you that crazy electrons can get through walls and would be used in kooky things like computers, silly little toys, life-saving medical devices, and personal picture phones. But those people found that electrons do go through walls, and we now exploit that effect every day, all the time. In computers, silly little toys, life-saving medical devices, and personal picture phones.
Here, let me help you.
I think I got this one handled, Ivan. Oh, and head on back. You're on soon. So, what will happen if Ivan can shrink his elephant? Well, I certainly don't know. No one knows. All we could truthfully say is that we'd have the smallest magnet ever known. My guess is that when we have it, we should expect the same things we'd expect if elephants could be shrunk to the size of peanuts. One could say it would be magic, but I think it would be better than that. It would be science, and whatever comes of that will be real. This is where it starts. Look, the collected works of Tolstoyevsky. Tolstoyevsky, good God. Jesus. Shakespeare.
You ready, Mr. Ari?
Yes.
Action.
Oh, hi there. Because I love it. I'm sorry, that was a little Valley Girl. Because I love it. Because I love it. Because I love it. Because I love it.
Hi, bud. You're a pretty neat trick.
Yeah, good. Hey.
Wait a minute, Ivan. You must have enough of those by now.
Peanuts, peanuts.
And line? Line? Line, that's a lot of
That's a lot of atoms. That's a lot of...
smoke.
Is that a focus? Nice to get that stuff off. Whoa, hello.
Here.
No, Ivan needs to keep going or something.
You film him filming us, filming the ending. So you reveal the whole thing. Because you're talking about it revealing...
It's the same material that's in plexiglass and lucite, but Ivan and his friends use it a little differently.
And on behalf of the Nanodot kids, we welcome you to When Things Get Small.
We'll be back.